Think way back to the ancient Egyptians or Stone Age man. Art was two-dimensional, flat. People drawing things on pyramids or caves only had two dimensions to think about. But then somebody came along. I don't know who it was who thought of it first, but they must have been really smart. They added another dimension. And all of a sudden, art became three-dimensional. Hi, my name's Kevin Burgess. I'm an organic chemistry professor. I do research and teaching in organic chemistry for undergraduates and graduate students. I've been doing this for ages, probably since the pyramids were built. I'd like to talk about representing molecules, because in chemistry, the way we represented them was similarly two-dimensional. And then somebody came along, probably more than one person, but I knew who one of them was, Sir Derek Barton, and they decided that three-dimensionality was important in chemistry. And they started thinking about conformational analysis. A new field was born. So this steroid, which we draw pretty much flat in this diagram, became three-dimensional, and we can understand how it reacts and what its shape is, and that governs biological activity. Many molecules have three-dimensional shapes. There's this antiviral drug, there's menthol, you know what that smells like. Limonene, you can probably guess what that smells like too. There's these secondary messengers which drive signals in your cells. There's many steroids like cholesterol, cholic acid, testosterone. All these molecules have three-dimensional shape. To understand how they react and how they interact with other biological molecules, we have to understand what shape they are. So this is universally important in organic chemistry and introductory organic chemistry. If you don't understand the basic shapes of molecules, you cannot get good grades throughout the course. So let's look at some fundamentals. You need to understand first of all what the shapes of the molecules are, and then you need to be able to apply this knowledge. Let's look at some fundamental shapes for organic chemistry. Cyclobutane. What shape is that? Well, it's a butterfly. Cyclopentane. What shape is that? Well, it's an envelope. Cyclohexane, the most important one of them all. What shape is that? Of course, it's a chair. But there's something funny about cyclohexane that's important. Like many of these other shapes, actually, it's not one chair, but it flips between two chair forms. So that's the second thing you need to understand about cyclic hydrocarbons. They're often in dynamic equilibrium between conformations. And there's a bit more you have to understand about cyclohexane, because it can get from one conformation to another via a twist boat, which is higher in energy, a high energy intermediate, or a boat, even higher energy intermediate. Okay, so if we understand that, then let's make the process a little bit more complicated. Let's load it up with substituents. If we put one substituent on a cyclohexane, it flips between equatorial and axial forms relative to the plane of the ring. If we put two there, can you predict which is the most stable one? Have you done this in sophomore organic already? Can you predict it now? Underemphasized in most sophomore organic chemistry courses is the effects of fusing two rings together. In other words, making them edge share a bond. The steroids, which I've already mentioned, have this edge shared bond. They have decalin arrangements, C10 arrangements of two six-membered rings. Now you know that a chair flips, and I put it to you that cis-decalin flips also. It flips both chairs at once. What about trans-decalin? If you've done this in sophomore organic chemistry, can you tell me if trans-decalin flips or not? It doesn't. What about this steroid? Can you identify the decalin that forms rings A and B and tell me, is it a cis-decalin or a trans-decalin? You might understand when someone tells you what a cis-decalin is and a trans-decalin, but you can't really answer the exam questions. So to learn how to understand and apply these concepts, you need problems. You need a lot of problems, and you need to be able to check your answers to make sure you're right. And you need to go over the ones that you don't get right. That's why I wrote my little workbook, a workbook with an attitude. It's all problems. It's not a textbook. You can buy it, download from Apple Books for about half the cost of a cup of coffee. It's one of a series of workbooks that I'm expanding regularly at the moment. with these workbooks, you can go over the lecture that you're just about to have or have had to study for the exam. Do you think you need it? Well, let me put this to you. In that workbook, I'll ask you about every concept and fact that I can think of in several different ways. I'll ask you with diagrams and words. I'll ask you using energy plots. I'll put in plenty of multiple choice questions. I'll use words and diagrams to test things together. See, the idea is that any way it comes up on your exam, you will recognize that format. Why do I call it byinquisition? Because every day our brains check on millions, even trillions of things. My brain is checking that this ceiling is not going to fall on my head. But tonight, when my brain undergoes night cleaning, when I sleep, it will push out all these superfluous facts. And if you're not careful, if you don't think about organic chemistry again, if you don't think about today's lecture, it will push them out too. So the next day, if you can go over the lecture again, active recall, and force your mind to try to remember, it's so much better for learning. Psychologically, it's a proven technique. If you download one of these workbooks onto your tablet of choice, this is you, by the way, you're writing in all the answers for that particular workbook. When you finish, only then do I want you to check the answers online. Sure, in between time, you can do detective work. You can look in a textbook, you can ask friends. I don't even mind if you search the web, but you have to work for the knowledge. Don't cheat by looking at my answers. And then after you've finished, check the answers that you've entered into the iPad, and any that are sketchy, any that are wrong, delete them. Let the day play out. Forget. Let the brain do its night cleaning. Following day, go over this again, particularly the blank questions without looking at my answers online, and see how many more you can get right. And then erase the ones that you didn't after you check against my answers online. Repeat this at ever-increasing intervals. Psychology says that's how you're going to learn organic chemistry or anything else, actually. So in that way, you're playing with the forgetting curve, because every time you input something into your memory and you forget it, but then go back and input it again, you forget it again, but you forget less. And the third time, you'll forget, but even less this time. And the fourth time, much less. And each time you go over this, active recall, you are remembering long-term so much better. So why do I call my books byinquisition? Because this is not easy. You have to force the brain to do it. It's not comfortable to sit there and think, what was the answer to that? And it's too easy to cheat. But if you cheat, if you look at my answers too soon, if you go online to avoid this torture, then the learning becomes invalid and the torture must begin again. Sorry to say that. Thank you very much for listening. Bye-bye.